Okay, last of the lesson videos for this unit. Sequencing Series Unit 7, Mathematical Induction. I'm going to tell you right now, these are by far the most difficult things to do in this unit. If you look at the statement above my head here, it tells that mathematical induction is used to prove statements about positive integers. An induction proof consists of 3 steps. It is a proof. Like back in geometry, it is a proof. There's a set of guidelines. There's 3 steps that we use for these mathematical inductions, these mathematical proofs. But that doesn't mean that they're super easy to do. I'm going to show you 2 examples in this video. These are not the only ways to do them. The 3 steps are what you have to work through. The 3rd step is where the difficulty lies. So let's take a look at one of our examples. First, let's talk about the 3 steps. Okay, so in any mathematical induction problem, the first step is show that the statement is true for some integer n. Typically, I want to show that it's true for the first one. If I can show that it's true for the very first value, I'm good to go. That takes care of that. The second step is the easiest of all 3 steps. All you do is you assume the statement is true for some integer we call k, such that k is greater than n. This assumption is called the inductive hypothesis. So I'm going to make a hypothesis and say, I'm going to assume this is true. And then the 3rd part is you have to show that the statement is true for the next integer, k plus 1. There's where the biggest difficulty lies, is right there in that part there. That's going to be the toughest one. Okay, so those are the 3 steps. We have to show that it works for some integer, and then we assume that it works for a value greater than the one we just had, and now we have to show that it's true for the one after the one that we just assumed was true. Okay, so let's take a look at one here. I want to prove that the sum of the squares of the first n positive integers is n times n plus 1 times 2n plus 1 all divided by 6. That is, I need to prove that 1 squared plus 2 squared plus 3 squared all the way up to n squared equals n times n plus 1 times 2n plus 1 divided by 6. That's what we need to prove. So I'm going to go through these 3 steps. So step 1, I need to show that this happens to be true when I have a 1. So when n is 1, I get 1 plus 1 plus 1, bracket 2 times 1 plus 1, all divided by 6. If I do that, I get 1. The sum, if n is 1, I get 1, because 1 squared equals 1. That is true. So step 1's okay. Step 2, I need to assume that 1 squared plus 2 squared plus 3 squared plus 4 plus k squared equals k times k plus 1 times 2k plus 1 all over 6 for some positive integer k, such that k is greater than 1, really, is what I should have on there. I didn't have that on there. Okay, so there's the first 2 steps. Those are the 2 easy steps. Okay, step 3. I got a statement here. I need to show that this given equation is true for any n equal to k plus 1. So I need to show that 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1 squared, I should have a k plus 1 squared there, delete that, plus k plus 1 squared would equal the whole thing. So I'm going to actually have the 2k squared plus n. So I'm going to add a k plus 1 squared to both sides. And what I want to show is that I'm going to get this thing to work out. So now that I have that, my next step happens to be to go ahead and add. I'm going to add this k plus 1 squared over here. So now if I do that, the first thing I have to do is I have to get a 6 in front of this. So I actually put a 6 up here. Oh, wrong marker. A 6 up here and a 6 down here. So now I had common denominators, and now I can go ahead and add, which is what I wanted to do. On this other side, I'm not doing anything with it. Okay, so now, what am I going to do now? I need to kind of do some factoring. I got all the stuff on the top. I need to do some factoring. And if I do the factoring, what happens is I get k plus 1 times k times the quantity 2k plus 1 plus 6 times the quantity 6k plus 1. So what I notice is the first term here, this set of terms, oh, let me use the highlighter. Okay, this set of terms had a k plus 1 in it right there, and this set of terms had a k plus 1 quantity squared. So I took the k plus 1 out, and I left all the rest of it inside a set of parentheses. So now that I have that, what I can do is I can do some simplifying. I can clean up what's inside the bracket. And if I clean up what's inside the bracket, I end up with k plus 1 times 2k squared plus 7k plus 6. I've got to simplify. Now, what I really want to do is factor out that 2k squared stuff. I want to factor that out. Well, if I factor that out using that long formula Mr. Armstead taught you, I get a k plus 2 and a 2k plus 3. So now I'm looking at this statement, and if I bring it back down so it's into the same formula that we had it before, I have my k plus 1, I got my k plus 1 plus 1, I got 2 times my k plus 1 plus 1. So here I have a formula that looks like my assumption back in number 2, but using a k plus 1 in place of that k. So here's what I say to finish this thing off. I say, okay, so my last expression is the right side of the equation to be proved, where n has been replaced by k plus 1. Thus, the equation is true for when n is equal to k plus 1. So I finish off the statement by saying, this proves that 1 squared plus 2 squared plus 3 squared plus n squared equals n times n plus 1 plus 2 times 2n plus 1 all over 6 for all positive integers n. So what I did was I showed that it was true when I put a 1 in. So I did my step 1. I showed it was true when I put n equals 1 in. And I got both sides to equal the same. I assumed this was a true statement with the k. Then I added what the next term would be on, ooh, there it is. I added that term on both sides. Then what I did is I cleaned up the right-hand side. So on this right-hand side, I just went through a set of steps and I cleaned it up. Now, I'm giving you reasons why I did each step, or my example did. That way you get an idea of how things were done all the way through this. Then I conclude with this statement. So here, the last expression, this expression right here, is that same formula, but using a k plus 1 instead of just the n that we have. Because this formula is for k plus 1, we prove that it's true for all of them. Okay, let's try another example. Okay, I want to prove that 7 to the nth power minus 1 is divisible by 6 for all positive integers n, for any positive integer n. So my step 1 is I have to prove it's true for at least one of them. I'm going to go ahead and put the 1 in. If I put a 1 in, n equals 1, 7n minus 1 becomes 7 to the first power minus 1, which is 6. And 6 is divisible by 6. So my statement is true when n is 1. Step 2, easiest problem of the world. Easiest problem of the system here. I'm going to assume that 7k minus 1 is divisible by 6 for all positive integers k. This means that there is a whole number r such that 7k minus 1 equals 6r. So there's the important thing right there. I make this assumption, and then if I can come up with this, it really helps. But I really don't need it. I can have that all crossed off. But sometimes it's easy to tell. If I know what that means, I can use it. Now that I know what that means, I can work with it. Okay, so my next step, I need to go to 7k plus 1. So I'm going to start with my inductive hypothesis, meaning I'm going to start with that equation, 7k minus 1 equals 6r. I'm going to start there. Now, what I'm going to do is I'm going to multiply both of those sides by 7 in this case. If I multiply both of those things, ooh, I missed something in here. Sorry, I'm going to add 1 to both sides. There we go. I knew I was missing. I want to get that 1 on the other side, get that 7k by itself. Now I'm going to multiply both sides by 7. And the reason for that is I get this, 7 times 7, okay, yada, yada, yada. I got that in there. All right. So now, with that being said, I can simplify. Basically saying 7 times 7k is 7 to the k plus 1 power. So let me delete that off. And on the other side, I get 42r plus 7. Okay. Now, my next step in this case is going to be, I want to subtract 1 from both sides. That way I can get it looking back like this other. So I want to get it to look like that. I want to get 7 to some power minus 1. I need to have that being shown. And then on the other side, when I subtract the 1, I get 42r plus 6. Well, from here, what I should be able to do is just this nice simple factoring deal. On this right-hand side, I can take a 6 out. And if I take a 6 out, I get 7k plus 1 minus 1 equals 6 times this quantity, 7r plus 1. Well, this part over here, and I'm already there, this part right here says that I got 6 times some quantity. That's important for us to know, because that means, since r is a whole number, we set that up above, 7r plus 1 is a whole number. Therefore, 7k to the k plus 1 minus 1 is divisible by 6. Thus, this statement is true for all n equal to k plus 1. So in step 1, if we go back and look at it, I showed it was true for 1. Step 2, I assumed it was true for some k value. And now step 3, I've just showed that it is true because this number right here happens to be a whole number. And if that's a whole number, that means I had 6 times a whole number, which means I could divide it by 6. So that means that statement is true there, which finally gets us to the point that, yes, I have proved that 7 to the n power minus 1 is divisible by 6 for all positive integers n. There's our second set of proofs. Notice the 2 problems that I had here were not done the same way. And that's part of the issue with this. These are going to be tough. Anytime they say you got to do something with divisibility, yes, this is the way you got to do it. When they're talking about some other problem, prove that this happens to be true, this is the best way to do it. Go ahead and add, oops, I thought I had that locked in place. Go ahead and add that next term to both sides and then clean it up. This is going to require that you know how to do some of your Algebra 1 stuff that we have not refreshed in a while. But there you go. I'm going to give you a couple of days to work on these, and I don't think I gave you that many problems either. But these are not the easiest ones to do. I can guarantee that for you, but I also know you are capable of doing them. Have good luck.